I know, they're gonna have to watch it online.
Okay, here we go. Alright, so okay, so what we're doing today, I want to, everybody, we got a lot to do. Turn and face front, please. Thank you. Thank you. Okay, I want to go through some not difficult stuff. I'm going to show you, and I'm honestly, I'm going to, any instruction I do, a lot of it's just going to be review and synthesis stuff you already know. It's just going to get sort of integrated right into the examples. We don't need a lot of like upfront explanation of this. You know these rules. It's just a different application of the same rules. What we're going to talk about is we're going to extend the stuff that we did at the beginning of chapter 6. Remember, we did some work with properties of exponents, and you did some assignments on that. You became intimately familiar with the properties of exponents. What we're going to do in chapter 7 is we're just going to take those same properties and apply them to rational exponents. Okay, and so nothing really changes. There's just a few little odds and ends that some other considerations that we need to look at when we're dealing with fractional exponents, but much of it is the same. This chapter deals with rational exponents and radicals, and the reason that I'm pushing this so hard is because when you try to simplify radical expressions, the best thing you can do is write them in terms of exponents, rational exponents, and use your properties of exponents. We understand those well. They're easy to manipulate. Radicals just look complicated. Okay, so let's go here. What we want to do with this, well, this first one's really simple. What do? You already know the answer.
You just add them together.
Yeah, just add them together. If we multiply like bases, we add the exponents. And so on this first one, we just end up with what?
5 to the second.
Yeah. 5 to the 4/3 plus 2/3 equals 5 to the 6/3. And what's 6/3? 2. So all you have to do, isn't that simple? All you're going to do is you're just going to write the powers in terms of rational exponents, fractional exponents, use the properties of exponents to combine the rational exponents, reduce the fractions, and that's it. Yeah. Yeah. Okay, so 25, right? Okay, what about number 2?
Wait,
Yeah, good. If we take, question?
when you multiply the numbers, when you multiply the 5s, you're not just
No. Because remember, when we multiply like bases, we keep the base and add the exponents, right?
So is it pretty much simplifying?
That's all it is. That's all we're doing.
So we're doing
The whole goal of
simplifying?
this, that's it. All we're doing today is we're just going to practice writing expressions in their simplest form. There's really no algebra. Okay? It's just review of kind of simplification stuff.
There's
I
no
mean, I guess
x's.
that's algebra.
We're going to have x's.
Yeah, but the x's, the variables make it a ton easier. You'll see that. The variables are just a piece of cake because the bases are so easy to recognize.
X.
It gets a little bit harder. It's x, y, or z or something like that. It gets a little bit harder with numbers to see when you have like bases and you have to, you'll see examples here. You'll know what I mean in a moment. So if we take a power to a power, our properties of exponents say we multiply the exponents, right? So we get 3 to the 2/3 times 1/2. We can cross cancel when we multiply fractions. And so this just becomes 3 to the 1/3, right? No big deal. Okay.
And that's just a cube root.
And it's a cube root. And if we wanted to write this for whatever reason, to me that's a better way to write it. But what if you wanted to write this as a radical, or if the assignment said write your answer as a simplified radical or something like that? Then that would just be a cube root is a 1/3 power is a cube root. So it would just be a cube root of 3. Okay.
But wait, because when you're multiplying them, wouldn't they get bigger, not smaller?
Not fractions. Fractions. What's 1/9 times 1/9? It's 181. It's a lot smaller.
I was thinking like if you were to make them all the same common denominator, it'd be. Never mind.
You multiply fractions straight across though. It's easier to multiply fractions than add or subtract.
The first one went up because the fraction was above 1. Right?
Yeah. Yep. Mm-hmm. Yeah. And they were added up there, right? Those fractions were added. Okay. All right. What about this next one? 4 to the 1/4. that looks simplified. It's not 1, but it looks simplified, doesn't it? But notice that the base here, see if you can tell me what the difference is in the base in problem 3 compared to the base in problems 1 and 2.
It's an even number.
Say it again.
It's an even number.
Okay, it's an even number, which implies what? What about the first 2 numbers? It's a perfect square. Yeah, it's got factors, right? The first 2 bases were prime numbers, 3 and 5, right? They couldn't be factored. But 4 can be factored. What is the prime factorization of 4? 2 squared. It's a perfect square, right? So we can trade the 4 for a 2 squared to the 1/4, which gives you 2 to what power? If I multiply those, you know, power to power, we multiply the exponents. What's 2 times 1/4? Yeah, it's 2/4, which is just 1/2. So it's a square root of 2. Okay?
Wait, what?
Wait.
Oh.
Make sense?
Yeah.
So the one after that, it would be 5th root of 8.
It's a 5th root of 8, and that you might think, okay, that can't be simplified, but it can't, because 8, what about 8? 8 is not a prime number, it can be factored, right? Yeah, it turns out that it is a perfect cube. And so we could write the 8 as a 2 cubed to the 1/5. So my final answer is 2 to 3/5, yeah. Okay, now, what if we wanted to write this? Here's another issue. That's a good way, that's a great way to write it. If you want to write this as a radical, there really are 2 ways you could do this that in my mind are equally good. What is that as a radical? Okay, so it's the 1/5 is a 5th root, right? So one way to write this would be as the 5th root of 2 all cubed. That's fine. The other way to write this would be, what if instead of writing this as the 5th root of 2 cubed, what if we wrote it as 2 cubed to the 1/5? So in other words, we take the power inside the radical instead of outside. We could also write this as the 5th root of 2 cubed, which is just 8. Right?
So will it take any answer, or does it want to be?
Well, it's, yeah, so on Moodle, it would consider any of those to be, you know, correct. But it might give you some direction, like it might say write it as using rational exponents. Or write it using a radical. In that case, if it said rational exponents, that would be correct.
Usually it says if it's like the same value, it says it's the correct value, but not specified.
Right, and that's what you get, right?
Wait, how did you get the 5/8?
The 5,
2 times 2. Oh.
how did I get this one, you mean?
Oh, yeah, I figured it out.
Okay.
Yeah.
What about 6 to the 1/4?
2.
Okay, does 6 factor?
No.
Well, it does. Factors into 2 and 3, right? So I could write this as, but that doesn't really help me, right? Because neither one of those is a perfect square or a perfect cube. If I tried to do that, I'd get 2 to the 1/4 times 3 to the 1/4, and that, I don't get any place with that. It doesn't help me. I'm not able to simplify that. I can't reduce any of the fractional exponents, right? And so we're just stuck with 6 to the 1/4. There's nothing there that really I can do to it to make it any simpler.
Oh, that's, so you can't.
Right, so my answer on this one is just 6 to the 1/4. The difference being that even though this factored, it didn't factor into anything that had a multiplicity greater than 1. Like this had a multiplicity of 3. It was a perfect cube. These aren't. This is just 2 to the 1 and 3 to the 1, and so it doesn't really do anything for me. Okay?
Would we have to enter it as 4th root 6 or not enter it like that?
Just it doesn't. I mean, the instructions will tell you.
Alright.
Yeah, they'll tell you which way to enter it. Okay, what about this guy?
Ooh. 8 times 64 is then just 2 1/4.
Okay, you could. Now
You
there's.
can multiply it and then flip the thing.
You can. There are a bunch of different ways you can go about this, but I want you to kind of look at this in a way where you can make this as simple as possible. Now, one thing we can do, we do have like exponents. And I could factor out a like exponent, couldn't I? Because I know from my properties of exponents that a times b to the m equals a to the m times b to the m. So I go either way with that, right?
Wasn't it n?
I could distribute the exponent to both bases if I wanted to. Or I could also, if I knew that I had the same exponent for both bases, I could factor that out and end up with something like that. So one possibility is I could write this as 8 times 64 to the 1/4. But yikes, 8 times 64 is a big number, right? That's gonna be hard to deal with. What I really kind of want to do instead is I want to pare this thing down to factor it down to where I can get the smallest possible base. Okay? So rather than doing that, I kind of want to just take each one of these individually and write them using smaller bases, and then we'll see if they combine in a way that's healthy for the problem, that makes it simplify. So let's see, 8 is what? 2 cubed. Yeah, okay. So this is going to become 2 to what power? 3/4, right? 2 cubed to the 1/4 would be 2 to the 3/4. What about 64?
4 to the 3/4.
Okay, it's 4 to the 3/4, but 4 is not prime. We could go further. Yeah, 64 is actually, sure, it's
2/5.
it's 4 cubed, but now think about that. If you're telling me it's 4 cubed is 2 squared cubed, so it's 2 to what power? 6. Yeah, 64 is 2 to the 6. So this one becomes 2 to the 6/4. Now that's helpful. I got like bases. What do my properties of exponents tell me there? Yeah, whoops. So I end up with 2 to the 9/4 is my final answer. If I wanted to write that as a radical, I could write that as what, the 4th root of 2,
Alex Chase,
To the
come to the
9.
office, please. Alex Chase.
or I could write it as the 4th root of 2 to the 9th, which would be 5/12. So I could write it either way. Okay? Doesn't matter. I mean, but if you see what I'm saying? Either one of those would be okay, but if you're writing it as a rational exponent, that's how you do it. Okay? Make sense? Okay. So we want to break it down. Because 8 was a perfect cube at a multiplicity of 3 and 64 was 2 to the 6th, we could break that down to much smaller bases, much simpler. All right. So next issue. Okay, now this is kind of we're taking a step here. This is kind of an important one. Let me remind you about something. When you did problems like this, let's say you had something, I'll make it real simple. What if you had 1 over the square root of 3?
Is that
You were asked to
2/7?
write that. Say it again.
What's the
Top is of 1.
1.
If you were asked to write 1 over the square root of 3 in its simplest form, what did you do? Multiply top and bottom by square root of 3. Good. And the reason we did that was so we'd end up with what on the bottom? 3. No square roots. Okay. That's simplest form because in math we prefer not to have irrational numbers in the denominator. So that's called rationalizing the denominator. We went from an irrational number that cannot be written as a fraction, as a decimal, it never repeats and never terminates, to a 3, right? So we need to do something like that because wouldn't you agree that what's on the bottom here, at least at this point right now, what's on the bottom is a 7th root? Okay, well this is just a 2nd root, right? Same issues are going to crop up potentially. So what could we do with this?
You would,
Ideas?
you could move the 5 to the 1/7 to the bottom.
Okay, so one thing we could do is we recognize that when we divide like bases, we just subtract exponents, right? And so we've got like bases here. Now, we had a little rule that we adopted in this class where we said that we want to keep the base where it has the most power and subtract the other exponent. So what's bigger, 4 sevenths or 1 7?
4.
4 sevenths. So we'll keep the 5 on the bottom. And then we're just gonna subtract the 1 sevenths from the 4 sevenths, right? Okay. That gives us 1 over 5 to the 3 sevenths. Okay, but that's a problem because I've got a 7th root on the bottom, right? So that is not fully simplified. What could I do? What do you think?
Could you multiply by, power of 7.3 over 7?
Okay, no, I can't, because, here's why I can't. Because if I take my answer to a power, aren't I gonna get a different value? Right? And I don't wanna do that, I want my answer to have the same, when I'm done, I should be able to type this answer into my calculator and get a certain decimal and type my simplified answer into the calculator and get the exact same decimal. Has to retain its value, yeah.
Would you type in the inverse of that power?
What do you mean the inverse?
So like 7 thirds, because they would cancel out, and 2 times it.
What about a negative?
Okay, no, the same issue, I can't really take anything to a power.
Would you like multiply it, like the top and bottom of 7 times by 5?
Something like that, yeah. Okay, we're moving in the right direction with this. What do you suppose I want to end up with on the bottom?
What?
Well, 5, probably, right? I probably can't get a 1, but at least I could maybe get this down to where I have a 5, an integer. Okay, good idea. That's what we did with the square root, isn't it? We started with the square root of 3 and ended up with a 3. Okay, so if I want to end up with a 5 on the bottom, what am I going to have to multiply by? 5 to the 4 sevenths. Everybody agree?
Why?
Okay.
Because
Because I need the fractions to add to 1. 5 is really just 5 to the 1. Okay, so I got to multiply 5 to whatever fractional power is going to give me an integer sum, right? So 5 to the 4 sevenths. Of course, I need to do the same thing on the top, though. I got to multiply by 1. So I end up with 5 to the 4 sevenths over 5. Okay? And then I can't, then I'm stuck. That's what I get. Now at least though, now I've got my radical or my root, whatever you want to call it, is on the top and I have an integer on the bottom. Okay, but could we have done this one a little more simply? Now my question is, did we really need to do this step right here? Maybe not. Maybe not. Maybe we could have done this a little more easily. Let's look at what I mean. Let's start with the same problem. Okay, we can already see, because the bottom is a bigger exponent than the top, that we're going to get stuck with something on the bottom, right?
Yes.
So why not just directly turn the bottom into a 5? What would I multiply top and bottom by to get a 5 on the bottom? Right? And then on the bottom, that's going to give me 5 to the 1. On the top, I get 5 to the 1 seventh plus 3 sevenths. So we can do it in one step. Okay? See? All right, now I'm going to throw you a curveball.
Strike 3.
Strike 3. What if we have 5 to the 4 sevenths divided by 5 to the 1 seventh? What do you think, David?
Can't you just move the 1/7 that's pointing to the top?
Yeah, and we're done. This is a much easier problem. See the difference? This time, the power on the top, the exponent on the top is bigger, and so we're not going to have the problem of being stuck with a fractional exponent on the bottom, right? This time we can just go directly to our answer, which is 5 to the 4 sevenths minus 1 seventh. 5 to the 3 sevenths, and we're done.
Whoa.
Right? Okay. All right. Okay, what about this? That looks pretty complicated, but it's actually pretty simple. The gotta see the trick though. You guys have already seen this trick once.
Like today.
Yeah.
The powers just cancel?
The powers don't cancel, but we have like exponents, don't. So if we have like exponents,
They cancel out.
they don't cancel. They don't cancel, but what can I do if I've got a product and or a quotient that involves, remember, let me go back real quick
Wait,
to,
what do you mean can?
I mean, where is this thing? I had it here somewhere. Maybe I erased it. I bet I did.
I know what.
I think I did. I think I erased it.
You would add the top two exponents,
What number?
subtract the bottom.
Yes, well, you know, you can't add the exponents, but remember our rule of exponents. If we, I'm gonna write it down here. So what, you tell me, what would you do if we had, a to the m times b to the m over c to the m?
Combine A.
Combine A and B to
Put C on
subtract
top.
C.
Right?
Oh.
You see? Now, I can't do that, now you gotta be careful. I cannot do that with sums or differences, right? It's not okay to do this. I can't say a to the m plus b to the m. I can't do this. You can't generalize this because this is a big problem. A to the m plus b to the m is not equal to a plus b to the m, right? That doesn't work. When you're adding or subtracting stuff, it just does not apply. But when you're multiplying and dividing, sure, it does, right? If you've got factors that are multiplied and or divided that have like exponents, I can undistribute those exponents, right? That's very helpful here, isn't it? So if I undistribute my 2/3, I can combine these bases. I can simplify the bases, right? They're all going to combine and simplify. I get what to the 2/3? Well, 6 times 4 over 3, which is what? 8, yeah. And what's 8 to the 2/3?
8, or cube root of 8
Cube root of 8 squared.
squared, so
4. Okay? How about that? Hey, what about this guy? We're shifting gears again, right again. Okay, this time we're starting off with radicals. But what I want you to see is that these are no harder. There's only one additional step. What do you do?
You would combine them so it'd be 4 through, a bigger number.
You could. We could combine these as a 4th root of 81. That's one
Yeah.
thing we could do. What's another thing we could do?
27 and 1/4.
Okay, good. So what's really helpful here is to write these as rational exponents, fractional exponents. So I'd write this as 27 to the 1/4 times 3 to the 1/4, and now it becomes like a problem we just did. Okay, the 3 to the 1/4 looks good, but 27, is 27 factored? Yes, sir. Right.
Well, I was just gonna ask, instead of writing the 27 on the 1/4, could you just say 3 to the 1?
Exactly, that's what we're gonna do.
Okay.
Right. So 27 is not a factored base. We can reduce that base. 27 is what?
3 to the
3 cubed. Yeah, so we could write this one as 3 cubed to the 1/4. That's 3 to the 3/4, right? Times 3 to the 1/4 is what?
Just 9
versus
plus 9.
3 to the 1, right?
Which is, and so it would all equal 9.
3.
Because it's 3 times 3 though.
No, it's 3/4 plus 1/4 is 1.
Because you.
Oh, okay,
Like,
never mind, never mind.
I'm gonna have to write that.
Okay. Okay.
Wait, was that a?
What were you looking at?
I asked that like.
What about this one?
It's just the square root of 5.
Same.
Yeah, how'd you get it?
Because you just multiply two roots together and it cancels out.
Okay, so we get 5 to the 1/4 times 5 to the 1/4, which is 5 to the 2/4, which is, okay, as that's a radical, that's just square root of 5. Right? Now, you guys are more than bright enough to probably skip right to that answer though, right? Because you can, in your mind, you can be thinking of this as 1/4, 5 to the 1/4 times 5 to the 1/4, and jump right down to that probably, right? I mean, it's, initially you probably write it down, but eventually you're gonna be able to make that whole jump, I bet. I think we can skip that one. Well, no, let's not. So what's this one? Okay, so 5 to the 1/2 over 5 to the 1/5.
Wait, I don't get how it's 1/2.
Because it's a square root, remember there's an invisible 2 there.
Oh.
Okay, square root is just a 1/2 power. Okay, so now what?
Wait, could you just multiply by 4 this or you
No, you don't have to, because why is this different? How come I don't have to, I mean, I could, but it's gonna be a long process. How come I don't have to worry about rationalizing the denominator here?
Oh, yeah, okay.
Because the denominator is gonna be 1, isn't it? The top it has a bigger exponent than the bottom, so we get sucked up to the top instead of being stuck on the bottom, right? So what do we get then on the top? We get 5, the base stays on the top, 5 to the what? 1/2 minus 1/5, which is just 5 to what? It's gonna be what, 5/10 minus 2/10, 3/10? Okay, now if I wanna write that as a radical, what are my choices? 10th root
5 to the 3rd.
of 5 cubed, or what if I put the power inside?
5 to the root, 6 to 125.
125, yeah, 5 cubed.
Wait, really fast, why is it 5 to the 3?
Because if I just subtract these, 1/2 minus 1/5, 1/2 is 5/10. I get common denominators.
Oh, okay.
1/5 is 2/10.
Okay, yes.
Okay. Okay.
That's our answer.
Yep. So this stuff isn't so bad, is it? Okay, what about, I guess that's a good one. I tell you what, we'll come back to this one if we have time. Really, we've done enough of this that I want to make sure we get to the other side. Okay, so, okay. Yeah. Okay, so whoops, wrong way. Okay, so what about this? Yikes. So if we want to simplify this, now remember when we're trying to write radicals in simplest form, our goal is to get as much out of the radical as possible. Like for example, you would have done stuff like this. You would have done things like, let's say, the square root of 75 simplified is what?
I know.
Wait, how did you get 75?
5 radical 3, yeah. Okay, does everybody see that? How come? Because 25 is a perfect square, and 25 is a factor of 75, right? We can break that down to the square root of 25 times the square root of 3. We never really got any more complicated. We never looked at it in a more sophisticated way than that previously for 2 reasons. First of all, we hadn't yet really made this connection. We hadn't really looked at rational exponents. And the other reason is because square roots are just easier. I mean, all you're looking for are perfect squares, and those are numbers that we're pretty familiar with. But not so much with perfect fifths, right? Can anybody tell me, make a quick list of the perfect fifths? I didn't think so.
75 or
Yeah.
What?
So that's not the way we want to do this. What we want to do instead is we want to break this down. We want to try to take that base and factor it, create a prime factorization and see if there are any factors with multiplicities greater than 1, right? So if we end up with some perfect cubes or something like that might be helpful. It might turn out, by the way, when you do a problem like this, that's already simplified. It might be. So let's practice this with 12:15. You haven't done this in a while, and you might have done this in different ways, and if you have a different way of doing this that works for you, that's fine. Here's how I do it. It's up to you. I like to just pick off the factors as I go. So what's one obvious factor of that number? 5. So we can break 12:15. We can break off a 5, leaving us with 243. Okay, what about 243? What's an obvious factor of 243? 3. But now let's be really smart about this. How do you know 3 is? Because you can add them together.
Is 9?
If you yes it is. You can add them together. Now this is a really good trick. We know that if you add all the digits together and it's divisible by 3, then 3 is a factor. But that also works with 9. Right? So if you can add the digits together and they add to a number divisible by 9, then 9 is guaranteed to be a factor. Well, that happens, doesn't it? 2 plus 4 plus 3 is 9.
But sometimes we'll add to 18.
Well, but that's fine. If they add to 18, then 18 is divisible by 9, right? So then we can break off a 9, leaving us with what? 9 goes into that, so we get 27. Okay, but now we can focus on the 9 and the 27. 9 is really just 3 squared, right?
3 times 9.
Okay, we get that down to a prime factor. 5 is primed, right? 27 is 3 cubed. And so what is the prime factorization then?
3 to
Should we
the
get-
5th.
Good, 5 times 3 to the 5th. Okay, everybody see that? Okay, that works great because we're taking a 5th root. So when we write this down, we're going to write this as 1215 to the 1/5. Well, 1215 is that, right? So it becomes 5 times 3 to the 5th to the 1/5. Hey, what's with the desk hockey going on over here?
Sorry,
Stop
someone
that,
switched
please.
back
No,
on.
I'm not. You're trying to switch me.
Okay, so if I distribute the 1/5 then, what's 3 to the 5th to the 1/5? Not 1.
3.
3. Yeah, it's the exponent's 1. It's 3 to the 1. So I'm going to get a 3 times 5 to the 1/5. You see that?
Wait,
3 and then 5 to the 5th.
The 5th root of 5.
Yeah.
That's it.
Wait,
Yes.
will you say that again?
Yes.
Top part? Okay.
Yeah, okay, so top part again. Now everybody focus here. So we got this thing broken down. The 1215 breaks down into 5 to the 1 times 3 to the 5th, right?
Yes.
I've got to distribute this exponent then to both parts. So what I get, 3 to the 5th to the 1/5 is 3 to the 5 times 1/5, 3 to the 1. Right, so we get a 3 that has effectively been liberated from the radical. It's no longer got a fractional exponent. It's an integer, right? What about the 5? Well, the 5 is to the 1/5, and so we end up with 3 times the 5th root of 5. Isn't that cool? Much easier way to do it, isn't it? Now, by the way, you can retroactively apply this to square roots too. Okay, so you can do the same trick for trying to simplify, big square roots as well. Oops, wrong way. Okay, what about this guy? Now, before you jump into this, take a second and think about this. I've got several options, but let's try to pick the best one. What do you think?
You could make them into, so it's 18 1/3 times 15 1/3.
Okay, that's a good idea. Let's keep these separate. You might be tempted to say, okay, well, I've got 18. If I've got 18 to the 1/3 times 15 to the 1/3, those are like exponents, which really just corresponds to like roots, doesn't it? So I could have combined those into one big square root, but 18 times 15 is a big number, 285 or something like that. So it's a big number. So we don't want to do that. We don't want to fight some big number in there, because all we're going to really try to do eventually is break down the bases into smaller, prime factorization anyway, right? So let's start with the 18 and the 15. 18 breaks down into what?
3 and 6.
Okay, 9 and 2, and 9 is really just 3 squared. Okay, so this becomes 15 breaks down into
3 and 5.
5 and 3. Okay, now, so if we just distribute that 1/3 to everything, then look what we get. We get 3 to the 2/3 times 2 to the 1/3 times 3 to the 1/3 times 5 to the 1/3. You see any like bases? Threes.
So you could just return them all into 1/3.
Yeah, so the 3 to the 2/3 times the 3 to the 1/3 just becomes 3 to the 3/3, so just a 3. Good. Now we are still stuck with a 2 to the 1/3 times a 5 to the 1/3 that we can't really do anything with, right? So what's our final answer then?
3 cube root 15, no, 10.
Times the cube root of 10, right? See how that works?
So
Take 3.
the 3 goes on the outside because.
Because the 3, when we broke this all down and we added up and combined the like bases, we ended up getting a 3 to an integer power.
Okay.
So we didn't have a fractional power, so that means it's outside the radical. Okay?
Well, and
Okay.
then we just multiply 2 and 5.
And then we have the cube root of 2 times the cube root of 5. And because we can't really take any of those out, we'll just combine those back into one radical. Okay, so here's I've saved the best for, well, do we need this one? Sure, let's do this one. Okay, how much time we got? 10 minutes? Okay, I think that's enough. Yeah.
You need 10 minutes to do this problem?
No, the next thing I'm gonna show you the greatest trick ever. This is an awesome trick, yeah. But I bet the next example.
Are you like gonna give us something that's so easy that has to do with this?
No, but it's something, but it's even better. You'll see. This stuff I've shown you the best way I know how to do this thing.
Wait, so the trick is.
Not for this stuff. It's for the next issue. Okay, what about this one though, real quick? If I break this up, I can break this up into, like any radical, I can split this into a cube root of the top and a cube root of the bottom, right?
Isn't it just 7 to the 1/3 on top?
It's gonna be, yeah, it is. Well, no, not quite, almost. No, almost, almost 2/3. Okay. What's 1 to any power? 1, right? And I kind of skipped a step there. I guess I skipped the step where we have 1/7 to the 1/3, then I can distribute to both parts, right? But in other words, we just get a 1 on the top. So we get 1/7 to the 1/3. Now this time we are stuck with a fractional exponent on the bottom. So what's our trick? Yeah, we multiply top and bottom by 7 to the 2/3. 7 to the 2/3 over 7. Okay? Okay, are you ready for the greatest trick ever?
Do it. That's our answer.
Yep. All right.
Ready for it.
Okay.
Okay. Greatest trick ever. Might just be the greatest trick ever. Okay, so what if I want to simplify this? I want to get as much out of the radical as I can. I want to write this as a radical in its simplest form. What power? Now you'll see why the variables are so simple here. What is x as a what power is that? If I write it as a fractional exponent. Yeah. So I get x to the 7/5. Here's the trick. If you write that power, that exponent, as a mixed number, look what happens. So this becomes x to what as a mixed number? 1 and 2/5. So your answer just becomes x to the 1 times times x to the 2/5, which becomes x times the 5th root of x squared. Okay, so here's how you can do this in one step. All you have to do is ask yourselves, you don't even have to write it, you can just do this in your head, I promise you. You can see that this is x to the 7/5, as a mixed number that's 1 2/5. And so your answer is x to the 1 2/5. Is that not cool?
Yeah.
Right?
Okay,
So in other words, the integer power goes outside, the numerator of the fraction goes inside the radical, and the denominator is the index of the radical. So let's take another example, and you'll get this.
make it easier.
Okay, no, I'll make it harder. You'll see. Watch.
No, how does having it simplified like that make it any easier to solve?
That's the answer. So if you're trying to write this as a radical in its simplest form, you're trying to get as much out of the radical as you can.
Right, but if we're trying to find x, that would just make it way harder, right?
Probably.
Oh,
Yeah.
okay.
Then why would we do it then?
It's a good question, but I mean, that's, if the point is, and that's really what we're looking at right now, is not solving anything.
That's simple.
We're looking at how to write things in their simplest form. Yeah, if you're solving it, that's just making it more
Yeah.
complicated. So you wouldn't do it, yeah.
So why would we ever do it?
Well, because it's a skill you need in math, you know how to do this. Okay, so what about this guy? Okay, look what we can do with this now. I'm gonna write through this once with all the steps, and then we'll do one of these where we don't write any steps down. You'll see how easy it is. Okay, so what if we have, like, if I write this out as a 1/3 power, I just get 16x y to the 7th,
16.
z to the 11th, all to the 1/3. If I distribute the 1/3, doesn't that just give me 16 to the 1/3, which is, by the way, what is 16? It's not,
It's a 4.
it's 2 to the 4th, right? So I could write this, let's just include that step, being as we're running out of time. So we'll write that as 2 to the 4/3, agreed? 2 to the 4th to the 1/3 times x to the 1/3 times y to the 7/3 times z to the 11/3, right? Okay, so now let's write our answer. The answer is always going to be some outside stuff that made it out times some inside stuff that got stuck inside the cube root. What about the 2's?
You can take
4/3 as a mixed number is what?
1 and 1/3.
1 1/3. So we get 2 to the 1. We wouldn't write the 1. But we get 2 to the 1 and 1/3.
Would it be like that line there times whatever's?
Yeah, the line is what's times, exactly. Okay, what about the x's? We get x to just the 1/3. That's 0 and 1/3. So we just get an x to the 1/3. What about the y's?
Y squared.
2 y squared.
Okay, so we're going to get y to the 2 and 1/3, z to the 3 and 2/3, 3 and 2/3, and I'm done.
That was actually easy.
It is. These are supposed to be the hardest, most butt-kicking problems they could make up, and if you use that trick, they're really simple. Now, wouldn't you agree that the hardest part of this, the exponent part, or the variable part is dead simple. The hardest part, if anything, is just that 16. It's just a number, right? Okay. Make sense? All right.
Trying to find the answer.
Can you ask us like a question to see who gets to go out early?
No.
No.
Jill, but what if?
Oh, I gotta take rolls. What I have to do?
You know,